Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to compute the moment of a couple, or in other words, a couple moment. So let's go ahead and get started. In the given information, we're being asked to determine the couple moment acting on the system by using two different methods. Part A asks us to use Cartesian vector notation, and Part B asks us to use scalar notation. So let's look at the given figure. Here we have a positive x-axis, a positive y-axis over here, and a positive z-axis up here. Now, what we have here is this three-dimensional bent pipe of some sort, okay? So we have this pipe segment that starts at the origin, O, and extends along the positive y-axis to point A. And then it is angled downwards in the negative z direction by 30 degrees. So you see this 30-degree angle here means that this pipe kind of has a bend or a kink in it, and it is angled downwards into the negative z direction there, okay? And the end of that pipe is point B. Now, at the corner A, we have a downward 50-pound force acting there. And then at the end B, we have an upward 50-pound force acting at that point. The length along the y-axis, which is OA, is going to be 3 feet long. And then the diagonal length from A to B is 2 feet long. And we also have here some projected lines to kind of help us visualize things. So this little corner right here is the projected line up to the XY plane, okay? So that's what we're looking at here. So how do we go about this? Well, if you remember, a couple moment is a moment that's caused by two forces that have the same magnitude, but they're acting in opposite directions. And that's what we have here. Point A has 50 pounds acting downwards, and point B has 50 pounds acting upwards. So these are two parallel forces acting in opposite directions, but they have the same magnitude. Now, a couple moment is also sometimes called a free vector. And what that means is it doesn't really matter what point we take the moment about, because in a couple moment, it is what it is. It's going to basically come out to be the magnitude of those opposing forces multiplied by a perpendicular distance in between those forces. So we could take the moment about point O for each of these 50-pound forces separately and add that together, and we will get a couple moment, okay? And our background information video explains that in a little bit more detail. And this example is supposed to exercise that. So let's go ahead and get started with a solution. Under solution, I'm going to start with part A here. And I'm going to say using vector notation, Cartesian vector notation. So in order to do that, what I'm going to do is I'm going to establish a position vector. And in fact, I'm going to establish two of them. So I'm going to use this yellow pin here. I'm going to establish a position vector from point O to point A, and I'm going to call that RA. And then I'm going to establish another position vector from point O down to point B, and I'm going to call that RB, okay? And so what I'm going to do is I'm going to find the moment about point O due to each of these 50 pounds using these two different position vectors and add it together. So watch what happens here. I'm going to say the couple moment is going to be equal to the summation of the R cross F terms for each of those forces, okay? So how do I do that? Well, I'm going to need these different R values, RA and RB. Let's go ahead and work those out. So those position vectors, RA and RB, you can hopefully just kind of look at this and figure out what those are. RA is pretty easy. RA is completely along the positive y-axis and has a length of 3 feet. So that's just going to be 3J. And of course, that has units of feet, okay? What about RB? RB, we have to do a little bit more work because we're looking for this 3D position vector, but we've covered that pretty extensively earlier in some previous videos, okay? So how do I get that RB? Well, I ultimately need the coordinates of B, okay? Well, point B is going to be located definitely 3 feet along the positive y-axis. But what about along the positive x-axis and the z-axis? Well, in order to get RB, I'm going to look at a 2D view to help me visualize this. So over to the side, I'm going to write 2D view. And I'm going to look at that angled pipe B from this viewpoint, okay? So I'm going to look at it from this direction in 2D. So what will I see? Well, I'm going to see this pipe segment here, and then I'm going to see my help lines. I have these help lines here and here, okay? And that's a right angle. Where's that 30-degree angle? Well, that 30-degree angle is right here, 30 degrees. And I know that this is my 2-foot length of my pipe segment, okay? So really what I need is this x value and this z value, okay? Well, I can just use basic right triangle trigonometry to get this x and z value. And you know what? That's going to give me what I need to find the coordinates of point B, which is right here. So this point B is the same as this point B. So doing some basic trigonometry, basic right triangle trigonometry, what will I have? Well, I'm going to have 2 feet times the cosine of 30 degrees. Let me color coordinate that a little bit better. I'm using black ink here. So 2 feet times the cosine of 30 degrees times I. And then we already know that the j component of point B is 3 feet j. And then the z component is minus 2 feet times the sine of 30 degrees k. All right. Now, again, how do I know that? Well, again, I'm just using right triangle trigonometry here. And I can be a little bit more specific. In fact, the z-axis, if I were to draw this, it would look like that, and then the x-axis is coming over here, all right? So working this out, what will I get? Well, I'll get RB is equal to 1.732 I plus 3j minus 1k, collectively with units of feet. So now I have my two position vectors, RA and RB. And remember, whenever we want to get a position vector, we always say the coordinates of the second point minus the coordinates of the first point. In this case, the first point where the tail of these position vectors are is at the origin. So that has coordinates of 0, 0, 0. So that's pretty easy to recognize. Now, what about these force vectors F? Well, that's the 50 pounds. And in particular, each of these 50 pounds is only pointing in one direction. They're both only pointing in the z direction. One is negative and one is positive. So how can I piece all of this together? Well, excuse me. Well, what I will end up having is C equals RA crossed with the negative 50 pounds, and that's going to have a K component. So here's that negative 50 pounds. So I have RA crossed with 50 pounds. And I'm going to say plus RB crossed with this positive 50 pounds. Okay? So plus RB crossed with positive 50 pounds in the K direction. So from here, I can set up two 3x3 determinants that I need to evaluate. So what is that going to look like? Well, we're going to have C equals, open up a determinant, I, J, K, 0, 3 feet, 0, and then 0, 0, negative 50 pounds. So that's the determinant for this first cross product. And then I'm going to say plus I, J, K, 1.732 feet, 3 feet, and negative 1 feet. and 50 pounds. Excuse me, I'm a little under the weather as I'm recording this video. So how do I evaluate these 3x3 determinants? Well, this is where we can use that technique where we recopy the first two columns to the right of each determinant and we perform several of those diagonal multiplications, okay? So why don't you pause the video now and you try to evaluate these two determinants on your own and make sure you know how to do that, okay? You need to know how to do this by hand, and I'll go ahead and write the solution right now. So pause it right now if you want to do it yourself. So ultimately, I get the couple moment vector as simply negative 86.6 J with units of pound feet. And it does have units of pound feet. It's still a moment, right? It's just a couple moment. So that is part of my answer. This is my answer to part A, okay? What about part B? Part B says to use scalar notation. Well, we'll find that using scalar notation is actually a lot faster for this particular problem. So my suggestion to you is whenever you have a problem where you can use scalar notation, I would use that instead of vector notation if you have a choice. This particular example asks us to do both, and that's why we're doing it, okay? So for scalar notation, guess what? We're going to pretty much utilize this type of figure again, this 2D figure looking in this direction at these two couple forces, okay? So what is that going to look like? Well, if I were to draw this out, I've got that diagonal pipe, I've got point B here, I've got point A here, okay? And I've got my right triangle there. I've got this 30-degree angle here, okay? And I have that 2-foot diagonal distance, and then I have those 50 pounds, right? Point A, it's pointing down, point B, it's pointing up. So there's 50 pounds here, and here's the 50 pounds here. So what I need is this perpendicular distance, okay? I need the perpendicular distance between the line of action of each of these forces. So how do I get this perpendicular distance? Well, that's just that distance x that we got earlier. That's this same distance x. So here's what I can do. I can say the magnitude of that couple moment is equal to F times a perpendicular distance. And so that's just going to be 50 pounds multiplied by 2 feet cosine of 30 degrees. And that's going to cause a clockwise tendency of rotation, clockwise tendency of rotation. So if I'm saying counterclockwise is positive, then this will be a negative here. And so when I punch this through, sure enough, I get negative 86.6 pound feet, okay? Now, if you really want to write this truly as a magnitude, right, then magnitude is independent of the direction. So if you were to really truly express this as a magnitude, you would just leave off the negative and say 86.6 pound feet, okay? But that negative is going to indicate a counterclockwise tendency of rotation when we are looking in this direction, okay, in 3D, this direction. Now, when we're looking in this three-dimensional direction, okay, what will our right hand do? If we use the right hand rule, you'll see that the fingers of your right hand will curl into the palm of your hand, and the thumb of your right hand will point in the negative y direction, which really still supports the fact that if we were to express this as a Cartesian vector, guess what we would get? We would still come out with the Cartesian vector negative 86.6 J pound feet, okay? So it's kind of cool to be able to to relate these two notations together, but obviously in this particular example, the scalar notation is a lot more user-friendly, okay? Well, that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.